Hey everyone, as promised in our last video for this course, we're going to talk about the second law of thermodynamics. The second law of thermodynamics is a statement about how closed systems behave. It just says that the change in entropy for a closed system will always be greater than or equal to zero. What does this actually mean though? To think about that, let's take a look at what we know about entropy. Entropy is a statement about the number of microstates that are available to a system. The example we gave last time is the box of gas, where there's a divider down the center and all the gas is shoved into one side of the box. When we remove the divider, the gas naturally expands to fill the entire box. But it doesn't expand to fill the entire box because it's impossible for all of the gas to be on one side of the box. In fact, it was originally on one side of the box, albeit with a divider holding it there. The reason that the gas expands to fill the whole box is because the macrostate with the gas evenly spread out throughout the entire box is much more probable than the macrostate with all the gas confined to one side. The reason is that there are just way more microstates that involve the gas evenly spread out across the box than there are microstates where all the gas is on one side. This movement from a macrostate with a small number of microstates to a macrostate with a large number of microstates always involves an increase in entropy. If you'll remember from last time, the equation for entropy just says that the value of the entropy for a system is equal to the Boltzmann constant times the natural log of the number of microstates available to it. And so to say that the entropy of a system is increasing is to say that the number of microstates available to the system is also increasing. As I said, this is a law of nature. It's called the second law of thermodynamics, well, for a reason. But it only applies to closed systems. Open systems can have negative entropy changes. For example, consider an air conditioning that's air conditioning your room during the summer. In order to do this, it's actually removing energy from your room and dumping it into the outside. This is causing the entropy of your room to decrease because the temperature of the room is decreasing. And as we saw in the last video, when temperature decreases, so does entropy. But crucially, your room is not a closed system. The air conditioner has to be plugged in to the wall, and it's constantly dumping hot air outside. In doing so, the entropy is increasing somewhere in the world, just not in your room. The increase in entropy somewhere else is going to be greater than the decrease in entropy in your room. And so the total entropy of the world is still going up, even though the entropy in your room is going down. Now, there's actually an interesting connection that we can make here to biology. Our bodies are fairly low entropy systems. They're pretty organized. If you just took all the atoms and molecules that makes up a human being and threw them into a bag, you could shake that bag for eternity and you would never get a human being popping out. That's because our bodies are fairly low entropy, and so a system of particles is never just going to naturally assemble itself into a human being. But crucially, our bodies are not closed systems. We're constantly bringing in things from the outside world. We're breathing, we're eating food, and drinking water. You can think of this a lot like the air conditioner in our room. Our body knows how to use the things that we give it to keep the entropy inside itself low. But of course, we then process everything that we take in and expel it as some sort of waste. The entropy of the waste is way higher than the entropy of the food that went in. And so while our entropy is staying low, the entropy of the world around us is constantly increasing because of our activity. But let's think about a closed system again. And let's think about a case that we've seen lots of times in this course. The case of two objects in a closed system that are at different temperature. We know that if we just leave the system closed and let it do its thing, the objects will change their temperature and eventually come to thermal equilibrium where their temperatures are the same. The reason is that the entropy of the system when the two objects are at thermal equilibrium is going to be more than the entropy of the system when the two objects were not at thermal equilibrium. And so over time, these objects are going to come closer and closer together in temperature. The entropy of the system is going to increase. And so saying that entropy always increases is really a statement about equilibrium. It just says that over time, any system that you can imagine, if it is closed, will eventually come to equilibrium, where everything's just sort of at the same temperature. Now, this is why I don't really like the framing of entropy as being disorder. When I think disorder, I think of a mess where things are totally different and flying all over the place. This is not the case with entropy. The macro state, where a system is at its maximum entropy, is pretty much the state where everything just looks the same. Everything is the same temperature, everything's sort of spread out evenly, and nothing interesting can happen. Now, in real life, there's actually only one system that is truly closed, at least as far as we can tell. That is the universe as a whole. The entropy of the universe as a whole is indeed increasing over time. Our current best theories about how the universe will end is that it will just increase its entropy until everything is exactly the same and nothing interesting can happen anymore. But you don't need to worry, that won't happen for an amount of time that is so big that it can't even really be comprehended. And that's it. That's the end of the topics that we're going to see in this course. We've covered quite a bit of ground here. We started by looking at conservation of energy and internal energies. We saw how energy can move from one form to another, and in fact will do so if given the opportunity. From there, we moved on to mechanical energies, things like kinetic energy and potential energy. We use that to figure out how particles will behave in bonds, and then we went back and built models for bond energy and thermal energy that take into account how individual particles will behave. That allowed us to understand where the numbers that we were using at the beginning of the course came from, like specific heat and the change in heat for a phase change. From there, we use that information to understand how gases will behave, how their temperatures will change when energy is added, how pressures and volume changes, and so forth. And then lastly, in the last few videos, we've seen one last little concept, entropy, that allows us to understand why processes happen in certain directions and not others. For example, we'll never see a case where you have a hot object and a cold object, and you put them together, and the hot object gets hotter and the cold object gets colder. It's not that this is strictly speaking impossible, it's just that it's vastly more likely for the hot object to get cooler while the cold object gets warmer. And there you go. That's all the topics that we've studied in this course. I hope that in watching these videos that you started to see why physics is kind of an interesting topic to study. We can apply it to all sorts of systems throughout the world. And even if you don't remember how to do calculations, my hope is that some of the key conceptual ideas stick with you, and that as you're going through your life, you can look at a system and be like, oh yeah, I remember, there's some interesting physics going on in there. Maybe there's some energy moving from one place to another, maybe there's heat going in or out of the system, or maybe there's entropy increases. Usually at this point, I'd say that's all for now, and I'll see you in the next one, but there isn't going to be a next video. So I thank you for the time that you spent watching, and hope you enjoyed it as much as I did. That's all for now, and I wish you well.